Hey guys, welcome back. We are back in the wonderful lab. We're having a great time. We just got some coffee, we got some lunch. It was Lebanese food today. Then I grabbed some coffee afterwards. Got some cold brewed iced coffee. It's a warm day today. It's not terribly hot, but it's fairly warm up there. It's warm enough to not get hot coffee. It's also not the morning, so it's not. It was cooler this morning. I think it was like 60 something this morning, actually. It was nice. Okay. So what are we doing this time? So we're back on the stream. Thanks for the follow. I appreciate it. Eisenday? Something like that? Eisenday. Whichever it is. Hey. Thanks for following the stream. I appreciate it. I don't even need this long. Okay, so what did we do in the first half of the stream? First half of the stream, first 2 hours, we went over writing benchmarks on GPUs and a little bit of CUDA programming. So what are we going to do the second half? Well, the second half, we're going to keep it pretty simple. It's mainly going to be a stream on hot takes and what else? What do we change the stream title to? Hot takes and we'll just call it hot takes on engineering and education. That's probably the best way I can put this. Hot takes on engineering and education. Isn't that just grand? There we go. Okay, so we're back. Let me take these headphones off. Okay. So what do we mean by hot takes on engineering and education? So there's a lot of subtlety that we could also bring this into politics too. Slightly into politics. I don't like to veer out of my lane too much. Engineering, education, and politics. I think I found the way to make the political system better, like how bills become laws. I think I've solved the riddle of the Sphinx. We've got it. We've got it down to a science now. Okay. So what's the first thing we're going to discuss? We should discuss... Let's full screen this. Let's go full screen, zoom in a bit. What do we got? Color we're going to write it? Let's write in green. In honor of our fallen comrade, Why So Green. We'll write in green. Sound good? In honor of Why So Green. If you don't know who Why So Green is, that was the original name that I had. Okay. So, hot take number 1. This is going to be on how does, let's see, what's the best way to put this? How does engineering, education need to change? And this is an interesting topic. It's an interesting topic because it's something that's I don't think is often thought about. I think that people think that we're at the stage of refinement, where we have a good idea of what engineering education is, and I think people have an idea of what engineering education should be, but I'm here to burst that bubble, because I think we have a bad paradigm for engineering education. Maybe this is specific to computer engineering, and that may very, very well be the case. But there's probably quite a bit Wait, you're Why So Green? Yeah, I'm Why So Green. This is, I changed names so that it would relate to the stuff that I cover. So I'm Engineering Today now. I'm Nick from Engineering Today, by the way, if you don't know who I am. Thanks for joining the stream today. Okay. So we're at this crossroads, right? So maybe computer engineering, which it's near and dear to my heart. It's what I'm doing a PhD in. Computer engineering, it's a very fast-moving field. And one of the things with fast-moving fields, so we should preface this with a why. So why does engineering education need to change? And maybe we'll figure out why it does, or if there's certain fields of engineering that maybe don't need to change, but maybe others do. Maybe we'll see that. So, Eisenday subscribed to the Tier 1 sub. Hey, Eisenday. Thanks a bunch. I really appreciate it. You're helping make this stream great. If you guys have any Twitch Prime subscriptions that you're not going to use this month, you're more than welcome to throw them this way as well. However, I wouldn't worry about it too much unless you like supporting the stream. Okay, so why does engineering education need to change? So let's look at a couple facts here. So let's take computer engineering as our, let's just pick one branch of engineering to start out with. So let's look at some facts about computer engineering. So one, it's fast moving. And this is because it's a fairly, there's what's known as mature fields or mature areas of study, and then there's ones that are fairly new or fairly young. And so this would be considered a young field. It hasn't been around that long. In fact, computers, the way that we classically think of them, really didn't exist until 1946 was when the first stored program computer existed. And if we want to think about computers and computer architecture, we generally have to think about the first stored program computer. A fixed program computer is not that interesting. It does one thing. A stored program computer is when we start getting to this idea of generality, where it's a program that can do an arbitrary number of things. So really this field has only existed since around 1946, when the first stored program computer was created, which was EDVAC. And that was at Princeton, and that was funded by, I think, IBM, and it was funded by the Army, I think. It was because the purpose of it was, it had a military purpose. The purpose was to calculate like ballistics tables, doing stuff like trajectory. So it's a young field. Mechanical engineering has been around for the longest time, since people have been designing things. But computer engineering is pretty new. And so let's see what this means. So it's fast moving. Things get outdated. And they get outdated at a pretty quick pace. So if we look back at something like way back in the day, things like Nixie tube transistors or whatever, those are completely irrelevant at this point. No one cares about them. And if we look back at things like even magnetic tape drives, magnetic tape drives are still used in some applications for huge amounts of information. Whether it's used or not ever again is another question, but it's used a lot in like cold storage stuff for large amounts of data. But for the most part, magnetic tape's dead. But there's this weird thing in computer engineering where it seems like you have to build a layer on top of a layer on top of a layer on top of a layer. And I'm here to say that that's just not true in a lot of cases. You don't need to build layer upon layer upon layer. you really just have to build an abstraction layer that says there's some things under here that do X, and that because they do X, we can just use them as this black box and allows us to do Y. It's this idea of black boxing things. So we have a box that does X. X takes inputs. We get those inputs, and it allows us to do Y. Now, the question here is, do we need to, do we need to know the specifics of X? This is a very interesting question. It's a question that really goes to the root of engineering education. And so, until now, the answer is yes. If you look at, I want to say 99% of computer engineering curriculum, you learn a lot of stuff that you will never touch again. And it seems like this is a very bad way to go around education. And it's not scalable. It's not scalable at all, actually. So if you look at something like, if you were to maybe quantify the amount of knowledge that you need at every single educational level. So let's say, this is not to scale. I don't have any actual numbers on this, but you can reason this out fairly well. So if you were to take a scale, do some let's do some pretend plotting here. And let's have on one side of things, so this will be the year, and then on this side of things we'll have let's say we can quantify the amount of knowledge you need to be a computer engineer, to be an electrical engineer, etc., etc., etc. So let's say that we're in the year 1950. Computer engineering basically just was invented. EDVAC does a great job. We're improving on it. We've got some new designs. We're not quite at the point where we're doing out of order execution yet, but we've got some crazy ideas that are kind of in the pipeline. So, when we're at this point, in order to be, let's do blue. In order to be maybe a computer engineer, you needed maybe this much knowledge. Okay. A fair amount, but it's manageable. Considering that the circuits for math back in those days, there was a lot of things that didn't exist yet. So things like parallel prefix adders didn't really exist. There was a lot of very, very simple circuits for arithmetic design, or very simple arithmetic circuits. So carry, not carry look-ahead adders, but carry ripple adders was still a reasonable design back in the day, just because transistors were so much bigger. Transistors didn't even exist in the 50s. But prior to transistors, when you were still working with like these much larger switches, the amount of switches you had to use was a really big part of it. So power was huge back in the days. I mean, they were warehouse scale computers. They weren't very powerful compared to today, but they were still warehouse scale computers. So you want to limit the amount of energy that you're spending. So some worse designs were viable back in the day. And we call them worse designs, but that's the baseline that we're setting is today. So you could get away with some pretty simple designs. They weren't efficient, but they were simple. Now let's take a step forward. Let's move into, let's say the 50s instead. And let's say the 80s. Let's say the 1980s. So the 1980s brought around a lot of change. So a lot of big ideas came out around the 80s. There was a lot of stuff on branch prediction. There was a lot of stuff on out-of-order execution and out-of-order completion, especially groups like from Wisconsin-Madison had a lot of papers during this time. A lot of famous people, Jim Smith, Guri Sohi, two people that I think won the Eckert and Mauchly Award, which is the highest award in computer architecture. They were both around during this time, and a lot of their big works came around in the 80s. But we'll notice something. We'll notice that there's a substantial bit more background that you have to have at this point. We care about performance now. We have transistors exist by this point. And so the amount of knowledge we need to be a computer engineer has increased a lot. So there's a lot more baseline fundamental understanding that we need. So let's fast forward again. So let's fast forward another 30 years. And let's say we're in the 2010s, which we are now. And there's been so many things that have happened since the 80s. Like I said, it's hard to quantify this, but the principle behind it is still true. So since the 80s, multi-core architectures came into existence. They didn't exist. GPUs, brand new thing, between the 80s and the 2010s. We did a lot of stuff with out-of-order execution in that time. Superscalar architectures, which is basically we're talking about multiple issue architectures. There's so many things that became standard in architectures at this point. And the problem is, it seems like we need to still go from the foundation all the way to this point to become a computer engineer. And so this graph, granted it's not to scale, and how can you really quantify how much information you need to learn, but it brings up an interesting idea, which is, do we really need to learn all of this information? Say info. And so I say no. And I'll get to why in a little bit. But the why is a little bit self-explanatory. But we can go into some concrete examples about why this is so